Welcome, computer science students. Our objective today is to map the systemic intersection of virtual reality and artificial intelligence. For years, software engineering treated these as separate disciplines. Watch what happens when we lock their architectures together. This integration replaces traditional interfaces with immersive environments that adapt to the user in real time. This creates a continuous convergence data loop. The rendering engines generate the simulation, while the inference models analyze the user's reaction to it, creating an infinite feed between presentation and logic. High-stakes fields are already deploying this architecture. In autonomous systems and medical training, the software trains human operators by analyzing and reacting to their micromovements. This architecture places the human operator directly inside the software's execution loop. In this environment, the security perimeter extends past the network and into the user's sensory and cognitive inputs. Safe engineering requires us to account for the cognitive impact of the software alongside its raw processing speed. Let's break down the structural hierarchy of this architecture. This animated diagram shows the three-tier presentation and logic stack of immersive systems. Tier 1 is virtual reality. These are entirely simulated digital worlds generated inside head-mounted displays, cutting the user off from physical input. Augmented reality differs by overlaying digital elements onto the physical world, maintaining the user's visual connection to their actual environment. Mixed reality is the critical bridge. It is an interactive blending where physical and virtual elements coexist and actively influence one another. Tier 3 acts as the reasoning center. Artificial intelligence, driven by machine learning and deep learning models, processes the complex inputs generated by the first two tiers. This reasoning center applies natural language processing and predictive algorithms to mimic human decision-making, interpreting how a user behaves within the simulation. When we merge immersive presentation layers with an active reasoning layer, the system generates intelligent virtual agents and simulations tailored directly to the operator's actions. This combination moves the system beyond a standard display, using its reasoning engine to actively intervene in the user's physical environment. To maintain that active intervention, the system demands an exponential increase in telemetry compared to standard applications. We can see that continuous exchange in this closed-loop flowchart. It tracks the exact data pipeline required to maintain a mixed reality environment. First, the system extracts highly sensitive telemetry from the human operator. This includes raw biometric signals and micro-behavioral patterns. That telemetry flows directly into the AI inference server. The model uses those biological inputs to calculate the optimal environmental response in real time. The AI then pushes a personalized, adaptive update back into the environment, subtly altering the simulation based on the user's physical state. This entire cycle must happen in milliseconds. If the data volume or speed drops, latency breaks the immersion and ruins the simulation. However, that exact pipeline structure exposes a glaring cybersecurity vulnerability. Because the system requires raw, unfiltered biological data to function, it acts as a massive repository of personal biometrics. This makes immersive pipelines high-value targets for data exploitation. The hyper-specific data required makes the entire architecture a security liability. These data pipelines are frequently applied in high-stakes human decision-making contexts, such as military training exercises or live cyber incident response. The intended function is straightforward. The AI analyzes the scenario faster than a human can and provides real-time predictions and recommendations to the operator. But placing a human inside a highly immersive simulation introduces a cognitive paradox. Look at this dual-axis line graph mapping system immersion against user reasoning. As the system immersion level increases, it artificially spikes the user's emotional response. Simultaneously, that emotional load actively suppresses their capacity for independent, critical, analytical thinking. This paradox creates three severe engineering risks. The first is over-reliance. Users overwhelmed by immersive data begin to trust the AI's recommendations without independent verification. The second risk is manipulated environments. Because the AI controls the simulation, biased training models can steer the user toward a predetermined choice by altering the visual feedback. The third risk is compromised data integrity. If a threat actor feeds incorrect telemetry into the loop, the AI will generate factually wrong but convincing environmental updates. During high-stress scenarios, these risks compound. A compromised system can overwhelm an operator's senses while feeding them false recommendations. AI within immersive systems must be strictly architected to assist human decisions. If the engineering induces cognitive overload, it replaces human judgment entirely. For computer scientists, preventing that cognitive overload requires a shift in perspective. Ethics are not abstract philosophical concepts, they are non-negotiable system requirements. We map specific ethical frameworks directly onto the vulnerable nodes of the data pipeline. This is the previous closed-loop flowchart, now fortified with 4 structural firewalls. Privacy acts as the first barrier on the outgoing telemetry stream, restricting unauthorized access to the user's raw biometric signals. Fairness must be coded directly into the AI node. This prevents algorithms from reflecting biased training data and producing unfair outcomes. Transparency governs the feedback loop. It mitigates psychological impacts by ensuring the user knows how the environment is adapting to them. The final barrier is accountability. This is the challenge of determining responsibility when the combined system causes harm. When these structural firewalls fail, the consequences are immediate. Unsecured architectures enable deepfakes, virtual manipulation, and targeted cyber attacks. Designing technology without integrated ethical frameworks creates unmanageable systemic risk that cannot be solved by simple downstream patches. Let's apply these concepts to a real-world stress test. A human operator navigating a high-stakes VR training simulation, guided by an AI decision assistant. This threat matrix cross-references the exact points of failure across the entire technology stack. A failure cascade begins at the logic layer. The AI algorithm contains an invisible bias, derived from compromised or incomplete training data. The presentation layer accelerates the problem. The immersive nature of the VR environment amplifies this bias, manipulating the user's emotional state and bypassing critical thinking. The failure reaches the real world when the mixed reality system forces the user to execute an incorrect, potentially harmful action based on their trust in the machine. While integrating VR and AI creates systems of immense scale, they are built on a technically fragile foundation. Building the next generation of computing requires looking beyond raw processing power to understand the direct cognitive impacts on the human operator. Safe deployment of integrated immersive systems requires technical precision, ethical awareness, and continuous human oversight. I am Dr. Alaa Jabbar Al-Maliki, and thank you for joining this lecture.